Calculus BC, we're now taking a look at section 5.2, building upon what we saw in 5.1. And let's read this paragraph. In 5.1, in that last video, delta x was fixed. That was the base of the rectangles. It was always the same. So we had an orderly way to find heights of rectangles. We had three methods: LRAM, RRAM, and MRAM. But what if delta x, which is just on a sub-partition xk minus 1, was not constant? Furthermore, what if the height wasn't necessarily found by a left endpoint, right endpoint, or a midpoint? What if it was found by w sub k, like a wherever x value somewhere between the endpoints, including the endpoints themselves? Also, what if f of x could be negative? Wow. Well, then we would get something that would look like this picture here. We would still have base times height with all of these rectangles. But look at this. You can see very quickly some rectangles have a very different base length. That base that I just highlighted is considerably smaller than the one between x1 and x2. Sometimes it looks like maybe we're using a midpoint method. Sometimes it might even look like more like we're doing a left endpoint method. And look here, our curve could go below the x-axis. Kids will quickly point out, wouldn't that mean that if I calculated an area here, base times height, if the height would be a negative y value, that would be a negative area value? Wow. Yeah. This is really what we'd have. This would be a Riemann sum. A Riemann sum, a calculation of all of these areas of rectangles summed up. But wow, how in the world could we come about this and actually, even most importantly, move from an estimate to actually calculating area or dealing with what would happen when we're below the x-axis, talking about that? Wow. Well, first off, we generally are skipping this section for the sake of time right here. I'm just going to briefly talk about it. The norm would be the biggest, the maximum base of a rectangle that you could ever have on a given partition. And if you found that, you could say, okay, this is the biggest base of a rectangle we could ever have. Well, look, if we really wanted to get the real area, or as we're going to hear in a moment, net area, we're going to say we'd want to have so many rectangles. We wouldn't be able to just have 5 rectangles or 2 or anything like that. We'd want a lot. So much that the biggest base of the rectangle would be approaching 0. Real quickly, students would think, well, that would mean that we'd need an infinite number of rectangles. Yes. Imagine if all of a sudden we'd have an infinite number of rectangles and we'd calculate all of these base times heights. That would be the real value of this integral. This is the second pillar of calculus, integral calculus. When you see, I'm going to rewrite this right here, from a to b of f of x dx, the dx is actually going to be identical to delta x. That's really the base of your rectangle. F of x would be your height. And we'd have a starting x value and an ending x value. That would define your subinterval. So, wow, we look at this. This right here is a way to measure not just an approximation of your area, but the real thing. Now, of course, kids will quickly point out, they'll say, well, you're talking about area. Hey, let's be realistic here. Your rectangles could go below the x-axis. You could wind up with negative areas of those rectangles. And indeed we could. So in terms of area, this definite integral can be interpreted as net area. It's possible that our answer could be negative, in which case we're saying that there's more area below the x-axis than above. And we very well could see cancellations of the positive area and the negative area, the area above the x-axis and below. So that's why really the proper understanding of a definite integral is that of net area. So let's just say that they wanted you to express a definite integral from -3 to 10. You'd have this integral symbol, almost looks like an elongated S. We're going to go from -3 to 10, and we could say, well, what's inside? Well, these W sub k's are really x's, and these are your heights. So you could say that's your function value. So that'd be -6x squared plus a cube root of x. Let me erase this and move that over. Plus 4 cosine of x dx. And this right here would be a way of saying calculate the net area. Now, how we're going to do that, we're going to have to go beyond this lesson. Today, we're just really thinking about it, introducing it, and trying to make some sense of it. Let's go to the second page here. First off, important properties. Important properties of integrals. Wow, is this an important one right here? Wow, super, super, super important. I want to really highlight this for you. If you were integrating from C to D, you're saying find the net area from C to D. It's the same thing as pulling a negative out in front and integrating from D to C. Now that can sound a little funny at first, but think about it. If you're reversing, if instead of going from like 3 to 10, you're going from 10 to 3, your delta x would have to be negative to get that. So you could just pull a negative out in front. And then that would always work out. Also, take a look at this one. This is a classic. It's actually delightful. Imagine if I said, calculate the net area from A to A of f of x dx. Well, imagine I said, calculate the net area on this curve from 5 to 5. You'd say area is two-dimensional. I can't make a rectangle. So that's just going to be 0. So let's take a look at example 3 together. This is going to be something for today at least. We don't know how to calculate the definite integral. We will next time, a very important lesson on the horizon. But as we're looking here from 1 to 3 x squared dx, let's just assume that the net area is 26/3. You'll figure that out. You will do that yourself next time in the next lesson. But wow, look at this. 3 to 3 of x squared dx. This right here is 0. See, that right there is this theorem right here. What's the net area from x equals 3 to 3? It's like imagine that you had an x squared and here's a 3, and you'd say, just go from 3 to 3. You're like, I could only draw a little segment. The width of my rectangle would be 0. Yep, that's just a 0. And then you look right here, you'd say, oh man, this looks so funny. Look, the 3 is down below. Tell you what, you could flip the bounds. You can always change the bounds, but when you do it, pull a negative out in front. That's what this red starred principle is all about. You're always able to flip bounds. Even if the bound below is the bigger one, you're always free to change them, just pull a negative out in front. But now what? You could say, well, actually, I know what this thing is. They told me that it's 26/3. That's like a gift. Final answer is -26/3. All right, well, let's go ahead and take a look at some great problems here. Evaluate the definite integral by regarding it as area under the graph of a function. So while right now we don't have a way to calculate this, that's coming very soon. But imagine that this is your y equals x minus 1. And while we could begin to try to work that out, we could say, well, at 0, we're down here at -1, right? By the way, if you plugged in x equals 1, 1 minus 1 is going to get you 0, isn't it? It's going to be right there. And wow, you could even keep going. You could plug in a 2. You could plug in a 3. At 2, you're going to be here at a 1. And then at 3, 3 minus 1, you're going to be over here at 2. So, of course, we've got a straight line. We've got a straight line there. It says evaluate the definite integral. We want not an estimate. We want the real thing. We want the real thing. So what you do quite frequently in a beginning integration kind of a setup is you work with geometric shapes. And we're going to do that right now. I've got my region below the x-axis. I've got my region above the x-axis. Look at that. And I've got 2 triangles. I've got 2 triangles. And you could say, okay, well, the area of a triangle, of course, is 1/2 base times height. So we're going to do this a lot. I'm going to call this region 1. I'm going to call this region 2. Let's see what we've got here. So the area of region 1, well, my base is 1. My height technically is -1. So you could say it's 1/2, 1. You want to put a -1 in there, you could. Other kids are going to go, oh gosh, no, Mr. Dobner, I just did 1/2 times 1 times 1. That's 1/2. But then area below the curve, I always convert to a negative. You can do that. You can do that for sure. Well, look, I've got area of figure 2. And you could say, well, this thing, wow, it's another triangle. Look at this base from 1 to 3. Well, you could do 3 minus 1 if you'd like. That's a 2. Look right here, that's a 2. So this is a base of 2, a height of 2. And the 2's cancel out here. You just have a 2 here. Area is above the x-axis, so it's definitely positive. Final answer is 2 plus -1/2. Add those together. Here's 4 over 2 plus -1 over 2. This integral is 3/2. Okay? So you'll get some problems where you're going to have to go back and use some familiar geometric shapes to help you. Let's take a look over here. This one can seem so peculiar. You look at this thing and you'll probably think, oh my gosh, how in the world am I going to work with this thing? You're telling me y equals radical 1 minus x squared, and oh my gosh, what is this thing? You know, it's not nearly as simple as a line. You're probably not going to see triangles here, and indeed you will not. Tell you what, I'm going to square both sides. I wonder why. Well, that's y squared equals 1 minus x squared. And then I'm going to bring my x squared over. And oh my gosh, this right here is the equation of the unit circle. Wow. You might remember we always had x minus h quantity squared plus y minus k quantity squared equals r squared. And you know, the center would be at h comma k. Your radius would just be not r squared, but just the r. And kids would go, oh, cool, this is a full circle. Actually, no, it's not. Be careful. This is a circle in this equation. You could say, look at that. You've got a radius of 1, it appears. You know, your center would be at 0, 0. Your radius would be 1. But notice, please, 2 things. First off, the reality is we're only going to go between 0 and 1. right? We're not going to go between x equals negative 1 to 1. We're only dealing with x going between 0 and 1. That's what these bounds are telling us. Second of all, y is the positive square root, because you're only dealing with this portion of the circle, right? And again, just to show you something, I mean, I hope that you've seen this time and again. And, like if you went to y equals, and well, we can just clear this all out and, more or less get the square root of 1 minus x squared. And, like if we just did a zoom decimal, just to get a friendlier window, you could say, hey, that, Mr. Dobner, what you said is wrong. Look, that's the top half of the circle. Yeah, but again, here we go. Remember, x only goes between 0 and 1. Right? X can't be negative here. It is really just a quarter circle. See, when y is a positive square root, it's only the upper half. So what do we really have for our area here? The area of this quarter circle is 1/4 pi r squared. So we'll have 1/4. Of course, our radius is just a 1. Wow, look at this. We will get pi over 4, and that would be our answer. Okay? So keep this in mind. That's a classic when you can see the equation of either a full circle or, in this case, a semicircle with the bounds that might become a quarter circle. All right, so let's keep going here and see if we could get a few things. Wow, what about if you had the integral from a to b of c? Well, I'll tell you what, if you just had a to b right here, and if you had a constant, this is a constant horizontal line. I think what I want to show you real quickly is you would get a nice rectangle for your area when you look at that. What would the base of it be? It would be b minus a. Your height would be c, so it would be c times b minus a. You're always welcome to draw a picture of that if you would like. That might just help you. When you're looking here from -1 to 4, I just said you could draw a picture. You could do that now too if that helps you. Look at this. You could say, well, here's -1, and over here is 1, 2, 3, 4, and wow, y equals 5. That's way up here. You could say, well, hey, I need to find my area. By the way, next time we'll have probably a very different approach to look at that. Well, how far is it from -1 to 4? Well, 5, End number, b minus a, so to speak. 4 minus -1, that's a 5. Look at that. The height here is 5. That's actually a square. Look at that. But following this template, it's 5 times 4 minus -1. That's 5 times 5 is 25. Okay? So hopefully that's making some sense for you. Couple other properties. If you ever have a constant inside, feel free to pull that out. You're always welcome to do that. If you have an addition of two integrals, you could turn that into the sum of these two separate integrals. Look at that. That's kind of cool. Do you have to do that? No, but that is a valid property. Likewise, if you have subtraction, you could say, well, that's from a to b of f of x dx minus from a to b of g of x dx. Okay, so we've got those. Okay, so good properties to know. We're going to keep referring to properties like this all throughout the year. And really, I think what you're going to see right here, we just have one last problem that we're going to have to take a look at. And wow, forgive me, I think something just went amiss. There we go. Let's take a look at the last page, the very last page. So what you're going to see is if A, B, and C are any three numbers, when you integrate from a to b of f of x dx, you're going to see that we can integrate from a to c of f of x dx plus from c to b. Now, I call this the barrel of monkeys theorem. We'll talk about that because it's almost like the barrel of monkeys toy. We'll have like a claw latching on, like one claw matches on to the other. It's like these two can blend together. So very often kids look at this and they'll say, okay, well, isn't it kind of common sense too with the way you would draw it, as if to say here's A, here's B, no, here's C in the middle, and then here's B. And if you had a curve that looked something like this, couldn't you say that from the integral from A to C, which might be this area right here, from C to B would be right here? You know, if you added those up separately, wouldn't you get the same thing as just going from A to B? Definitely, you can see that. But that might be the most obvious application that you can see. Here's a really cool application, though, that you can apply right now. Look at example 7. Expresses one integral. Well, right now, I don't have that barrel of monkeys idea where you've got a number up on top, a number down below. But wait a minute, I've got that minus right there. Tell you what, I'm going to flip the 3 and the 8, and I'm going to pull a negative out. Wow, that could look so weird. Kids could look at that and say, why are you doing that? Well, now, these match. Even though 8 is larger than both of them, this still holds true. Look at that. I can latch those two together, and I can turn this into the integral from -1 down below, 3 up high. Look at that. Here is one integral that would represent what we had earlier. Wow. Closing thoughts. If f is positive, of course your net area is positive. If f is always greater than or equal to 0, your integral must be greater than or equal to 0. Also, if f is bigger than g, what you will naturally see for every x in that closed interval, the integral from a to b of f of x dx will be greater than that of g of x dx from a to b. So that's lesson 5.2. Hope this is going well for you. Very excited to pick back up next time and dive into these problems in more detail.